Hello students, now I am planning to discuss the problems associated with first unit. In first unit, we have discussed all the necessary theory in our regular classes and the problems, numerical problems that we are going to discuss in this session, and all of you practice well. Definitely there will be problems in your regular FAT exams as well as in our main exam. So practice these problems carefully, students, so that you can comfortably solve the problems. There will be 16 to 20 marks in your hand if you practice these problems. That's why I am separately recording this video, and I am posting it to you. You can refer this whenever you have doubts or whenever you want more clarifications. You can refer this video, and it will be available for you always. And then in this session, there will be problems, preliminary problems, and also with little criticality, with little difficulty. So all types of problems I am planning to discuss here. The theory behind these problems already we have seen in our regular classes. So please recall that theory and you follow this video so that you will be very comfortable in solving all these problems. So this is the content we have discussed in our regular classes. You can see these are all the topics. Almost all topics are theoretical theory only. There are few topics. Only in those topics you will be having the numerical problems that I am discussing here in this session. That is Pascal law, Darcy's equation, Darcy's Weisbach equation, and we have losses in walls and fittings. We have a pump performance. In this particular topic, we have wide variety of problems. Please practice all these problems. I will start with very simple problems, and I will discuss almost all university questions here. So already we have discussed the Pascal's law in the class. Let me just recall that P equal to F by A. So this is the Pascal's law, and this is the definition. This Pascal's law is also known as the principle of transmission of fluid pressure. So fluid, it is associated with only fluid pressure, and this is beautifully defined like this: a pressure change occurring anywhere in a confined incompressible fluid is transmitted throughout the fluid such that the same change occurs everywhere. So in within a confined container, or within a confined environment, we can say, where we have incompressible fluid, that is normally hydraulic fluid, is transmitted through the fluid such that the same change pressure change occurs everywhere. So the pressure will be available every point in this confined environment, and that will be a constant, throughout the volume, or we can say the area. A change in pressure at any point in the enclosed fluid at rest is transmitted undiminished to all points in the fluid. So this is the Pascal's law. Already we have discussed this enough in our regular class. And now, based on this simple equation, F by A, P equal to F by A, we are going to see few numericals, and then we will move to Darcy's Weisbach equation, where we are going to estimate the losses in pipes and fittings, and then we will move on to pumps. In pumps, there are many problems and few important questions which are actually appeared in our earlier university question papers that I have taken up and I am going to discuss here. So first problem, a hydraulic press has a small piston of area 0.01 meter square and a large piston of area 0.5 meter square. So there are two pistons. The piston is having this area 0.1 meter square, 0.01 meter square, and large piston is having 0.5 meter square. So almost it is bigger than this 0.01 meter square. If a force of 100 Newton, force is also given here, is applied to the small piston, calculate the force exerted by the large piston. So this is a very simple problem, and we can equate. So P1 and P2, P1 equal to P2. So because Pascal's law, everywhere the fluid pressure is equal to same. So F by A. So that will be varying here. So here Pascal's law is P equal to F by A. So P1 equal to P2. So with that concept, we can say F1 by A1 equal to F2 by A2, and substituting the given values 100 by 0.01 equal to F2 is the unknown force. So that we are going to calculate for piston 2. So that is the F2. And equating this, we can get F2 equal to 100 into 0.5 divided by 0.01, that is equal to 5000 Newton. So on piston 2, the force available is 5000 Newton, and is the simple answer. Just using F by A relation, we can find this very easily, students. Next, we have a hydraulic brake system consists of a small piston with an area of 0.005 meter square and a large piston with an area of 0.02 meter square. So here also we can comfortably apply our Pascal's law. If a force of 50 Newton is applied on the small piston, calculate the braking force exerted by the large piston. So large piston force, like earlier problem, we can easily find. So F1 by A1 equal to F2 by A2. So 50 divided by 0.005 equal to F2 divided by area. Area is second piston area is 0.02. So F2 can be calculated. It is 200 Newton. That is obviously braking force exerted by the large piston. It is a normal force acting on the large piston, but it is called here as braking force. Just don't get confused. You can solve for F2 directly. So coming to problem 3, a hydraulic pressure shown in figure below. So this is the figure, and the diameters of plunger. So this is plunger 70 mm, and the ram is 150 mm. Diameter of ram is 150 mm respectively. Find the weight lifted by the hydraulic pressure when the force applied at the plunger is 900 Newton. So here force is applied 900 Newton, and here what is the force available at the ram we have to find. So here we know the diameters 70 and 150 mm. So we can find this is A1 and A2. With available diameter we can easily find the diameters, sorry, areas. And here F1 by A1 equal to F2 by A2. So same relation we can use, and F1 is 900 Newton is already available, and D1 is equal to 70 mm, that is 0.07 meter, and D2 is 150, and A1 equal to pi by 4 D1 square, and A2 equal to pi by 4 D2 square, and F2 weight lifted to be determined. So this F2 we have to find. Very simple question. And once you find A1 and A2, F2 you can easily find. So you have to calculate the A1 and A2 now. So here apply the same Pascal's law, right? F1 by A1 equal to F2 by A2. So substituting those values, you have to find A1 and A2, and this is A1 0.00385 meter square, and A2 is 0.01767 meter square. So now this is for, if you solve this for F2, this is equal to 900, and this substituting those values, and here F2 is equal to 4134.54 Newton, and in terms of kilonewton it is 4.13. So very easily you can solve this, students. It is a 5 mark or even 2 mark question. So you have to be thorough with the formula, and don't get confused with the terminology they use like in earlier problem. find breaking force. It is normally acting on the second piston or second area, and that force it is called as in different way, but don't get confused and you solve for your regular parameters. So Darcy-Weisbach equation, we have discussed this in our class. Let me introduce that again. Here, friction is the main cause of energy losses in fluid power systems. The energy lost due to friction is transferred into heat, which is given off to the surrounding air. The result is loss of potential energy. So I have explained all these things in our regular class. Just recall that. So potential energy in the system. So potential energy is the energy of the object that possesses by the virtue of its position. And when it is released from that position, then it will be in movement and it will acquire the kinetic energy. So here, and this shows the loss in the pressure or head. The head loss HL in a system actually consists of two components. One is losses in pipes, losses in fittings. So this is the Darcy-Weisbach equation. HF equal to 4FLV square by 2GD. F is the Darcy-Weisbach friction factor. It is a friction factor, dimensionless. It is a constant. And L is the length of the pipe. D is the pipe inside diameter. V is the average fluid velocity. And G is the acceleration of gravity. And we can see problems on this. Find the loss of head due to friction in a pipe 400 millimeter diameter and 2 kilometer long. The velocity of water in the pipe is 1 meter per second. Take coefficient of friction as 0.006. So this is again very simple problem. You can apply this Darcy-Weisbach equation, and this is 4FLV square by 2GD, and here the HF head loss that we have to find, and F is the Darcy-Weisbach friction factor. It is 0.006, so that is the coefficient of friction 0.006, that is a constant, and L equal to 2 kilometer, that is 2000 meter. D equal to diameter of the pipe, it is 450 millimeter, 0.45 meters. Always you convert into meters, and the velocity is 1 meters per second. So velocity is 1 meters per second, and G equal to acceleration due to gravity. It is a constant 9.81 meter per second square. So substituting all those values in HF equation, Darcy-Weisbach equation, we are getting the head loss is equal to 5.44 meters, and 5.44 meters is the head loss due to friction. So this is the answer for this simple question, and a straightforward question. You can substitute all the values and you can easily get the value, final value. So problem 2. Find the loss of head due to friction in a pipe of diameter 850 mm required to carry water with a velocity of 0.95 meters per second up to a distance of 1600 meters. So take coefficient of friction is equal to 0.01. So here the Darcy-Weisbach equation directly you can apply, and HF is equal to F equal to 0.01. It is given here, coefficient of friction. So 150 is L is the pipe length 1600 meter, and D is the pipe diameter 850 millimeters. Convert that into meter 0.85. V is the water velocity 0.95 meter per second. G is the acceleration due to gravity, that is 9.81. So this already we know. Please remember this value, students. So to solve this problem, so we know the Darcy-Weisbach equation, and substitute those given values, and once we substitute, and we are going to get the final answer, that is 3.47 meter. So 3.47 meter is the head loss. Head loss in terms of meters. This is the final answer for this simple problem. Problem number 3. It is observed that the difference of heads between the two ends of a pipe 250-meter long and 300 millimeter diameter is 1.5 meters. So here the heads difference between the two ends of a pipe 250-meter long and 300 diameter is 1.5 meters. So head difference is given here. Taking Darcy's coefficient as 0.01 and neglecting minor losses, calculate the discharge flowing through the pipe. So given data is pipe length, pipe diameter, and head loss, that is 1.5 meters. Darcy's friction factor is 0.01. So this is friction factor 0.01 is constant. Using the same Darcy's Westphal equation, 4Fl V square by 2GD. So V is the viscosity of flow, that is meters per second, and G is 9.81 meter per second square. So this is a constant value we have to remember. And the rearranging for V, so that is V, that is velocity we need to find. And here you can see the V, it is root square hf 2gd by 4fl. So by arranging this, and here it is V square, that's why we have root here, and hf into 2gd divided by 4fl. So that is the rearrangement of this equation. So here V is found, discharge Q can be calculating using A into V. So A into V, area, and V, and V is the velocity. So with these two, Q discharge can be find out here. A is the cross sectional area, A equal to pi d square by 4. So we know D is 0.3. By substituting all these values, so velocity is equal to 0.94 meter per second, and the Q can be computed now. So A can be calculated, and once you find A, Q can be calculated directly, and AV equal to Q. So Q, after substituting all the values, we are getting the Q value is 0.0664 meter cube per second, or in terms of liters divided by 1000, that is 66.4 liters per second. So in both ways you can give your answer. So next problem, a reservoir has built 4 kilometers away from a college campus having 5,000 inhabitants. Water is to be supplied from the reservoir to the campus. So here the college campus, so these many people are inhabitants, that is the people using that water. So water is supplied from the reservoir to the campus. It is estimated that each inhabitant will consume 200 liters of water per day, and that half of the daily supply is pumped within 10 hours. So calculate the size of the supply main if the loss of head due to friction in the pipeline is 20 meters. So that is HF is given. So friction factor is given 0.008. So that is Darcy's equation, Darcy's constant. So given data L equal to 4 kilometer, that is equal to 4,000 meter. Number of inhabitants are 5,000. Water consumption per person per day equal to 200 liters, that is equal to 0.2 meter cube, and the pumping duration is 10 hours. Head loss is given, that is 20 meter, and DAS is factor 0.008, and we can calculate the daily water demand. So daily water demand is number of inhabitants into consumption per person, that is equal to 5000 into zero point 0.2, that is 1000 meter cube of volume. Since half of the daily supply is pumped in 10 hours, so Q pumped, that is the daily supply, 1000 divided by 2. So that is 500 meter cube. And now you can compute the flow rate. You can compute the flow rate. So this is volume of pumped divided by time taken. So that is the time duration. So it is equal to 500 divided by 10 into 3600. So we are getting Q is now 0.0139 meter cube per second. So this is the flow rate. And Darcy's-Weisbach equation to determine the pipe diameter. So now we know HF equal to 4FL V square by 2GD. So D can be computed using V equal to Q by A. So Q divided by pi D square by 4. And now substituting this in Darcy-Weisbach equation. So the Darcy-Weisbach equation can be rewritten by substituting this V value. So V, that is V square here. So Q pi D square by 4 into that is to the power 2. So now d power 5 is equal to 8FLQ square divided by pi square GHF, and now d can be computed like this: HFLQ square divided by pi square GHF to the power 1 by 5. So this is the d. So now if you substitute all the values in this d equation, now final d equation, we can get the d value is 121 millimeters or 0.121 meters. So intermediate steps I have not shown here. You can solve and you can check the answer. So this is the right answer. If you are not getting this answer, please check with me. So next is Reynolds number. So already I have introduced this Reynolds number in our regular class. So with this number only we are going to decide whether the flow type is laminar, turbulent, or it can be transition. So these are the three types of flows we can decide using the number, this number. Reynolds found that the transition from laminar to turbulent flow in a pipe depends not only on the velocity but also on the pipe diameter and the velocity of the fluid. This relationship between these variables is commonly known as Reynolds number. So Reynolds number is equal to Vd rho by nu or Vd by V. So inertial forces divided by viscous forces. So this is the Nr. So using any one, or rho by nu equal to that is nu by rho equal to V. So that way also viscosity, by knowing viscosity also we can compute this. So V is the velocity of the fluid, capital V. D is the characteristic length, it is normally diameter. Rho is the fluid density. Nu is the dynamic viscosity. V is the kinematic viscosity. So kinematic viscosity is equal to nu by rho. So it can be shown that Reynolds number is a measure of the ratio of inertial forces to viscous forces in the given flow. So with this, you can say the number, once you know the Reynolds number, it is obviously a dimensionless number. And if it is lesser than 2000, it is known as laminar flow. If it is 2000 to 4000, it is known as transition flow. If it is greater than 4000, then the flow is known as turbulent flow. So the K factor, it is a friction factor. In addition to losses due to friction in pipes, there are also energy losses in valves and fittings such as T's, elbows, and bends. So these are all the elements in the pipes and fittings. For many fluid power applications, the majority of the energy losses occur in these valves and fittings in which there is a change in the cross section of the flow path and a change in the direction of flow. So normally this majority of the energy losses occur due to two factors: when there is a change in cross section or when there is a change in direction of flow, there will be losses in fluid flow. And already we discussed this. I am just revisiting the same thing what we discussed in our regular classes. The nature of the flow through walls and fittings is very complex. As a result, experimental techniques are used to determine these losses, and here this is HL equal to V square by 2G. So here this is K factor. This K, it is actually derived from the Darcy-Weisbach equation only. So now this is the constant of proportionality K is called as K factor. It is also loss coefficient. It is loss coefficient of the valve or fitting. So next we see a few more problems, and here the kinematic viscosity of hydraulic fluid is 0.0001 meter square per second if it is flowing in a 30 mm diameter pipe at a velocity of 6 meters per second. Find the head loss due to friction in units of bars for a 100-meter smooth pipe. The oil has a specific gravity of 0.090. What is the Reynolds number? Is the flow laminar or turbulent? So here we have to find Reynolds number, and also we have to find the head loss. Head loss. So both we have to compute. It is also one of the important questions. So given data, kinematic viscosity is 0.0001 meter square per second, and pipe diameter is 30 millimeters, that is 0.03 meter. Viscosity 6 meters per second. Pipe length 100 meters. Specific gravity Sg, that is zero point 0.9, and the acceleration due to gravity, as we know, it is 9.81 meter per second square. Density of water rho 1000 kg per meter cube. So density of water, you have to assume this, and this is normally a constant 1000 kg per meter cube for pure water. Please remember this value also. So compute the Reynolds number. So this is Vd by V, and 6 into 0.03 divided by 0.0001 equal to 1800. So it is 1800 is obviously lesser than 2000. It falls under laminar type flow. So here this is laminar flow, and then compute the friction factor for laminar flow. So we have to find the F factor, and here F equal to 16 divided by Re. So 16 divided by Reynolds number, so that is 16 divided by 1800. So it is F is equal to 0.00889. So compute the head loss using Darcy-Weisbach equation 4FL V square by 2G D, and substituting those values, we are getting HF value is equal to 21.75 meters. So next we have to find the head loss. So head loss to be converted into pressure loss, and in terms of bar we have to find this. The pressure loss delta P is equal to rho GHF. So we know rho G, and density of oil rho equal to Sg into rho of water, and this is 0.90 into 1000, that is equal to 900 kg per meter cube, and substituting those values, so delta P can be find out. It is 191.95 kPa in terms of kilopascal, and 1 bar equal to 100 kPa. So we can convert into bar. So 191.95 divided by 100 is equal to 1.92 bars. So this is the final answer in terms of bars. So head loss, pressure head loss is equal to 1.92 bars. So this is the final answer. So Reynolds number is 1800, flow is laminar, head loss due to friction equal to 1.92 bars. So this is another important question, students. So next, students, we have discussed a variety of equations in our regular class on solving the problems on pumps. We have not solved problems in the class. That's why I am recording here. And these are the very important equations. And if you remember this, you can solve any problem in the pumps. And moreover, the gear pumps are very important, and the vane pumps also important questions. I have chosen a few university questions, and I have solved here. I have given you all the equations. I have explained all the equations, those already discussed in the class, and please recall those equations and remember them. Once you remember, the problems are very simple to solve. So let us solve problems on our pumps. So already we discussed the theory, equations, everything in the regular classes. We are going to see numerical problems here. So the first thing is volumetric efficiency. In most of the problems, we are going to solve the volumetric efficiency. We have to get it. Already we discussed these equations in our class, and I am just revisiting those equations here. The volumetric efficiency indicates the amount of leakage that takes place within the pump. So here this involves considerations such as manufacturing tolerances and flexing of the pump casing under design pressure operating conditions. So here volumetric efficiency is equal to actual flow rate produced by pump QA by QT and theoretical flow rate pump should produce, so that is QT. So QA by QT is equal to volumetric efficiency. So volumetric efficiency typically runs from 80 to 90 percentage for gear pumps, 90 to 92, 82 to 92 percentage for vane pumps, and it is very high in the case of piston pumps, that ranges from 90 percentage to 98 percentage for piston pumps. So these values, please remember, once you solve the question in the exam or in FAT exam, wherever, you can cross check your answer. If the efficiency, volumetric efficiency, if it is not lying within these ranges, you have to cross check your answer, students. So that is another way you can cross check your answer. So mechanical efficiency indicates that amount of energy losses that occur for reasons other than leakage. So mechanical efficiency are the other type of efficiency. So that is actually without considering the leakage. So it is not relevant to leakage, and this includes friction in bearings and between other mating parts. So this can be calculated. Pump output power, assuming no leakage, divided by actual power delivered to the pump. So on metric units, so P QT by TA into N. So here the mechanical efficiency is the ratio of theoretical power output of the pump to the actual power supply to it. So pump P is the pump discharge pressure. So this pressure at which the pump discharges the fluid, and QD is the pump theoretical flow rate. The ideal volume flow rate of the pump, meter cube per second, or GPM, gallons per minute. So TA is the actual torque delivered to the pump. TA is the actual torque delivered to the pump. So if we know these parameters, we can calculate the mechanical efficiency. So N is the pump speed in terms of RPM or radians per second. So these are the parameters we should know to calculate the mechanical efficiency. So here mechanical efficiency in terms of torque also we can calculate. So that is the theoretical torque required to operate pump divided by actual torque delivered to the pump, that is TT by TA. So here this is QA and this is QT and this is QA. So QA is coming out of here. So this is the theoretical discharge and this is the actual discharge. theoretical and actual discharge. So here it is a simple diagram. So that shows the in terms of torque. So this is the TA and this is TT. So this is the actual TA and the TA can be calculated using, if you know mechanical efficiency, you can calculate TA. So theoretical torque can be find out. So any one parameter out of these three, if you know two, other one can be calculated. So please remember this equation also, students. So next, TT, theoretical torque, can be calculated using VdP by 2 pi. So Vp by 2 pi. So this is actual torque. Actual torque can be calculated actual horsepower delivered to the pump into 63,000 divided by N. So please remember this relation. And TA can be calculated actual power delivered to the pump in terms of watts divided by N. So this can be RPM or radians per second. So where N radians per second equal to 2 pi N by 60. So radians per second, if you want to convert into RPM, you can use this relation. So all these relations, please remember, then you can easily calculate the parameter that is required in the given question. So overall efficiency can also be represented mathematically as, so actual power delivered by the pump divided by actual power delivered to the pump. So these are the two. In other way, we can calculate this overall efficiency in terms of volumetric efficiency and mechanical efficiency. So here overall efficiency equal to QA by QT into PQT by TAN. So here if we know the volumetric efficiency and mechanical efficiency, directly we can calculate overall efficiency. So here overall efficiency is equal to actual power delivered by the pump divided by actual power supplied to the pump. So here in this way also you can calculate the overall efficiency. So we see few problems here in our regular classes. I have given you the enough theory part, so that theory can be used here, and also whatever relations that I have given here and in classes, please make a list of formulae, students. To solve all these problems, very simple, you prepare a list of formula, and if you remember those formula, you can solve any problem. See, first duty you have to do here is, please prepare list of formula. Once you prepare that, the rest of other things, solving the problems and understanding the problems, will be very simple. And we will see the first problem. A gear pump has a outside diameter of 100 millimeter, inside diameter 80 millimeter, and a width of gear 25 millimeter. If the actual flow of pump is 95 lpm, liters per minute, and pump speed 1440 rpm, what is the volumetric displacement, theoretical discharge, and volumetric efficiency? So we have to find three parameters. One is volumetric displacement, theoretical discharge, and volumetric efficiency. So these are the three parameters. So given data is outside diameter d naught equal to zero point 0.1 meter, inside diameter 0.08 meter, width of gear is also given W 0.025 meter, pump speed 1440 rpm, actual flow rate equal to QA, so that is given 95 lpm. So liters per minute, that can be converted into meter cube per minute. So now divide by 1000. So you have to divide by 1000. So it is equal to 0.095. So first we calculate VD, volumetric displacement. So that is equal to pi by 4 d naught square minus di square into W. So substituting these values, VD equal to 3.1416 divided by 4. So that is zero point 0.1 square minus 0.08 square into 0.025. Vd equal to 0.0000707 meter cube per revolution. So it is in terms of revolutions, and Vd equal to 7.07 into 10 to the power of minus 5. So this way you can write. So theoretical discharge Qt, the theoretical discharge is given by Vd into N. So that is Qt equal to the same Vd into 1440. Qt is 0.1018 meter cube per minute. And then volumetric efficiency can be computed. We know QA and QT, and QA by QT equal to volumetric efficiency. So that is equal to 93.33%. So here 93.33% of theoretical flow, and while remaining 6.67 is lost due to, that is this is the volumetric efficiency importance. So here it is gear pump. So here within the range, already we have seen the gear pump range. So this is 6.67 percentage is lost. So volumetric volume of fluid is lost in the pump. So that is the meaning for this theoretical, for this volumetric displacement calculation. So that was, sorry, volumetric efficiency calculation. Next, second problem on same gear pump. A gear pump has an outside diameter 82.6 millimeter, an inside diameter of 57.2 millimeter, and a width of 25.4 millimeter. What is the volumetric efficiency if the pump flow is 1800 rpm? It is also a very similar problem like earlier problem, and the rated pressure is 0.00183 meter cube per second. So given data is outside diameter d naught, so that is 0.0826. So outside diameter 0.0826, and we have inside diameter 57.2, that is 0.0572 meters. Width W is given 25.4, 0.0254 meters. Pump speed 1800 rpm. The rated flow, that is actual, rated flow is always actual. Students, please remember 0.00183 meter cube per second. Calculate the theoretical flow rate. The theoretical displacement per revolution for a gear pump is given by, so here this is pi by 4 d naught square minus di square into W. So substituting these values, Vd equal to 0.0000708 meter cube per revolution. So now theoretical flow rate is can be calculated. Q2 can be calculated Vd into N. So N is 1800 rpm, that is given in the problem. So already we know Vd already we have calculated. So on substituting this, we are getting Q theoretical equal to 0.1274 meter cube per second. Now calculate the volumetric efficiency, that is QA by QT into 100. So that is equal to 1.44 percentage. Volumetric efficiency of this pump is equal to 1.44 percentage. So a gear pump has an outside diameter of 100 millimeter and a gear having a module of 4 millimeter and 20-degree pressure angle with a 20 mm width. It delivers 80 liters per minute of oil while operating at 1800 rpm at a pressure of 10 megapascals. The actual torque of the prime mover is 100 Newton meter. So torque is given. So here pressure angle is given, students. No need to get confused. We are not going to use this 20-degree pressure angle. It is not required. But addendum is given. So these are the two parameters we have to calculate. Overall efficiency of the pump, theoretical torque required for the pump, addendum equal to 1 into module, redundum equal to 1.25 into module. M is nothing but module. So M is 4 millimeter, that is given in the problem. So we can calculate A value, D value, addendum value and redundum value. Outside diameter D naught equal to 100 mm, that is 0.1 meter. Module equal to 0.004 meters. Pressure angle 20 degrees, not required for any of our calculations. Width of gear L equal to 20 millimeter. Actual flow rate QA equal to 80 LPM. So that is liters per minute. So that we are converting into meter cube per minute. Meter cube per minute. So divide by 1000. So divide by 1000. So 80 into 10 to the power of minus 3 meter cube per minute. Pump speed equal to 1800 RPM. Operating pressure equal to 10 MPa, that is 10 into 10 to the power of 6 Pascal. Actual torque of prime mover TA equal to 100 Newton meter. Addendum equal to 1 into 4, that is 0.004 meter. Redundum equal to 1.25 into module, 1.25 into 4 equal to 5 millimeter, 0.005 meter. So now we can calculate the pitch diameter dp. So dp equal to d naught minus 2 into addendum plus dedundum. So dp can be calculated, and that is nothing but 0.082 meter. So here next step is calculate theoretical flow rate qt. And the formula for calculating the theoretical flow rate is qt equal to pi by 4 into d naught square minus dp square into L into P. Already we know dp square, dp already we have calculated. So substituting these values, qt equal to, it is coming here, that is 0.0926267 meter cube per minute. Then volumetric efficiency, that is the first parameter we have to calculate in this problem, that is QA by QT into 100. So volumetric efficiency is equal to 80 into 10 to the power of minus 3 divided by 0.0926267 into 100, that is equal to 86.36 percentage. So mechanical efficiency is equal to PQT by 2 pi NTA. So substituting these values, so we are getting 81.89%, 81.89. So this is the mechanical efficiency for this problem. And then overall efficiency we have to find. So we know the mechanical efficiency, we know volumetric efficiency. So overall efficiency can be find out with NV, that is the volumetric efficiency into mechanical efficiency. So we can calculate this. It is 70.72 percentage. Then theoretical torque we have to calculate, that is T by TA. So theoretical torque is TT, that we have to find out. We know the mechanical efficiency, we know TA, TT can be calculated, and TT can be 81.899 Newton meter. So this is the TT value. A vane pump. So next pump we are going to see a vane pump. Has rotor diameter 7 centimeter, casing diameter equal to 10 centimeter, vane width equal to 5 centimeter. It delivers 25 liters per minute of oil at 1440 rpm, having an eccentricity of 0.015 centimeter. Find the volumetric efficiency. Rotor diameter, that is dr equal to 7 centimeter, casing diameter is equal to 10 centimeter, and the vane width equal to 5 centimeter, eccentricity is 0.15 centimeter, and flow rate equal to 25 lpm in terms of meter cube per minute. We can divide by 1000, and the speed equal to 1440 rpm. So first list down all the formula so that it will be very easy to find out the answer. So N, that is the volumetric efficiency, equal to QA by QT. So QT equal to VD into N, and volumetric displacement VD equal to pi by 2 DC plus dr into E into W. So eccentricity and also vane width we have to multiply. So VD equal to 20.0277 centimeter cube, and QTH equal to VD into N. QTH can be calculated like this. It is 0.0288 meter cube per minute. So this is QTH. So volumetric efficiency can be calculated QA by QT. So that is equal to 0.86669. So that is 86.69 percentage. So that is 86.69 percentage. So next problem, an axial piston pump has 9 cylinders with a 15 millimeter diameter bore arranged on a 150 millimeter pitch circle diameter. So that is known as PCD, pitch circle diameter. It operates at 3200 rpm and delivers 190 lpm at rated pressure. Find the volumetric efficiency of the pump. So theta equal to 15 degree. So it is piston pump, and that is the inclination is given, that is theta 15 degree. So given data, number of cylinders equal to 9, that is small n, bore diameter dp equal to 15 millimeter, pitch circle diameter d equal to 150 millimeter, speed equal to 3200 rpm, flow rate equal to 190 lpm, that is QA is 190 into 10 to the power of minus 3 in terms of meter cube per minute, and inclination angle is 15 degrees. So now list down all the formula for a piston pump. Volumetric efficiency, it is as usual QA by QTH or QT. So QT equal to VD into N. So volumetric displacement N into A into D into tan theta. So this is volumetric displacement. VD you have to calculate using this formula, and VD equal to the same. Theta is known, and n small n is known, that is 9, and dp pitch circle diameter, that is 150 millimeter into d. So after substituting all these values, we are getting VD equal to 63923.2166 millimeter cube. So in terms of meter, you can convert and write or proceed. So QTH equal to VD into N. So QTH equal to 204.55 into 10 to the power of 6 millimeter cube per minute. So that can be converted into 0.20455 meter cube per minute. So now this is volumetric efficiency QA by QTH. So that is equal to volumetric efficiency is, after substituting all these values, it is coming as 92.88 percentage. So volumetric efficiency we are finding as 92.88. So please highlight this answer so that you will be getting full marks in the exam. A pump operates at 1000 rpm with a displacement of 100 centimeter cube. At a pressure of 70 bar, the input torque from the prime mover is 120 Newton meter. If it delivers 0.0015 meter cube per second of oil, determine overall efficiency of the pump, theoretical torque required to operate the pump, volumetric efficiency. So VD equal to 100 into 10 to the power of minus 6 meter cube, QA equal to 0.0015 meter cube per second. So speed equal to 1000 rpm, and pressure equal to 70 into 10 to the power of 5 Pascal. Input torque. So here pressure is given in terms of bar. You convert that into in terms of Pascal. Input torque TA equal to 120 Newton meter, and you have to find these three elements: volumetric efficiency, theoretical torque, and overall efficiency. These are the three things we have to find here. Now list down all the formula. And the volumetric efficiency QA by QT, overall efficiency PQA by 2 pi and TA, and mechanical efficiency equal to TTH by TA. So QTH can be calculated by substituting all the values. We know VD and we know N, and VD and N, once you substitute, you are getting 90 per, the QTH equal to 1.7 into 10 to the power of minus 3 meter cube per second. And now if you know QT and QA is known, and we can calculate the Q, that is volumetric efficiency. So this is 90 percentage, and the overall efficiency can be calculated, the mechanical efficiency into volumetric efficiency. And the mechanical efficiency we have to find first, and substitute all the values in PQTH by 2 pi and TA. So once you substitute this, 94.70, that is mechanical efficiency we are getting here, and the overall efficiency, mechanical efficiency into volumetric efficiency, then it is 113.64 Newton meter. And these are the answers. List all the answers, and we can show answers separately, so that the evaluator will be happy on seeing your answers, and he will give you full marks. So please practice this. So next question: a pump has a displacement volume of 98.4 centimeter cube. It delivers 0.00152 meter cube per second of oil at 1000 rpm and 70 bar pressure. The prime mover input torque is 124.3 Newton meter. Determine overall efficiency of the pump, theoretical torque required to operate the pump. So here T we have to find, and also overall efficiency. So given data is VD is given 98.4 into 10 to the power of 6 meter cube. So 9 centimeter cube to meter cube we are converting here directly. Flow rate QA is given 0.00152 meter cube per second. Speed is also given 1000 rpm. So P is 70 into 10 to the power of 5 Pascal. Input torque is 124.3, and TT is unknown. We have to find theoretical torque, and list down all the formula first. So QA by QT equal to volumetric efficiency, overall efficiency equal to PQA by 2 pi and TA, mechanical efficiency equal to TTH by TA, and here volumetric efficiency can be found out easily, and this is 0.00163 meter cube per second, and volumetric efficiency is 92.68. So QTH you have to find. So once we find QTH, all volumetric efficiency is 92.68, and mechanical efficiency, substitute all these values. QTH already known, and the remaining parameters are also given in the problem statement. Substitute all those parameters, we are getting 86.03 percentage as mechanical efficiency. Overall efficiency is mechanical efficiency into volumetric efficiency, 79.73 percentage, and the mechanical efficiency is already known, and we have to find the theoretical torque. So theoretical torque equal to mechanical efficiency into TA, that is 106.9353 Newton meter. So final answers are theoretical overall efficiency, theoretical torque. You write separately and show to examiner. So next problem: a pump has a displacement volume of 14 centimeter cube per revolution and runs at 2000 rpm. It operates against the maximum system pressure of 15 megapascal. and the volumetric and overall efficiency of the pump are 90% and 80% respectively. Actual flow rate, determine the actual flow rate delivered in liters per minute, the power required to drive the pump, and the drive torque at the pump shaft. So these are the parameters we have to find. So given data, displacement volume, it is 14 centimeter cube per revolution. That is in terms of meter cube per revolution. We can convert this. Speed 2000 rpm, pressure 15 megapascal, volumetric efficiency 90%, overall efficiency 80%. The QA actual flow rate we have to find. QTH equal to, that is VD into N. So QTH can be find out easily, and then we can find the volumetric efficiency QA by QTH. From this relation we can find QTH. So QA is, can be find out, it is 0.90 into 0.000466. Once you know QA, so QA is find out here, then find the power. We can find the power required to drive the pump. So power equal to 6.3 kilowatts. So 6.3 kilowatt P into QA. So that is P, that is 15 is already known, and then 15 into 10 to the power of 6 into QA. Whatever we have found here, QA value substitute here, and this is 6.3 kilowatt. Find the drive torque at the pump shaft, TA. So that is equal to P by omega. So omega equal to 2 pi n by 60. So it is rotational speed. So that is equal to 2 pi into 2000 divided by 60. It is equal to 209.33 radians per second. So then TA can be find out. So P by omega. So that is 6300 watts divided by 209.33 radians per second. So that is omega. So this is TA. TA is the final drive torque. Drive torque at the pump shaft is equal to actual torque. This is nothing but actual torque, that is equal to 30.09 Newton meter. So final answers are here. You list down this. Actual flow rate equal to QA 0.00042 meter cube per second. Power required is 66.3 kilowatt. Torque at the pump equal to, that is the actual torque equal to 30.09 meters. So these are the final answers. You write in this way, and for this you can refer our books, Anthony Esposito. These are the reference books we can refer. These are very standard books, Anthony Esposito and James L. Johnson. These are the two very good books you can refer. We stop here, students. These are the problems associated with our first unit. Please practice these problems, and formula, very important. You remember all the formula so that we can easily solve any problem that will appear in the exam, students. Thank you. We stop here. We see again in our regular class. Thank you, students.